Welcome to this video. So in this video, or the goal of this video is to get familiarized with important multi-threading concepts in Java and what are the important topics from interview perspective. So I do have some videos in my another playlist, but that videos were separate. So I'm combining all of them videos, plus there are some new concepts I have explained in this video. So we will be covering basics of concurrency, then how to create a threads, and what is Java memory model, what is difference or significance of volatile, synchronized, and atomic variables, what is thread local and what is inheritable thread local, and when to use, what are the scenarios, and what are different thread pools, what is Java executor service, what is thread pool executor. So these are really important from the interview perspective as well as the concepts perspective if you really want to deep dive into multi-threading. And then we will discuss about producer consumer problem, and we will then try to create millions of virtual threads which are lightweight threads and which was launched in Java 21. And then we will go through some important interview questions like a Daemon thread, a deadlock, starvation, livelog, and what is a fork join framework. So we will be seeing some of the important interview questions in the end of this video. So please watch entire 70 to 80 minutes video. So in 70 to 80 minutes you can really get all the knowledge, all the value you need to answer multi-threading questions in your interview. So let's get started. Before jumping to multi-threading, let's first discuss the single tasking, like how it used to work. So we all know like CPU can handle one task at a time. Okay, so in old machines we used to have only one CPU, and what CPU will do, it will handle one task at a time, and once this is completed and then maybe it will handle another task. So nothing was in parallel, so it was all single tasking in this case. So slowly we jumped into multitasking, so where CPU is handling one task at a time, but it is switching between application or between programs or tasks, right? So what CPU will do, so CPU will give some time to this task, and then it will give some time to this task. So it gives you an illusion that multiple tasks are happening at a time, but in background operating system and CPUs are working together so that they can switch between the applications or tasks, so that it can give you the feel that all the things are running in parallel, but that is not the case. Okay, so it's like a switching between tasks. Some time will be given to this, then directly CPU and operating system will give time to this. So that's how it works. So this was like multitasking. So this was multitasking, and this was single tasking, right? Single task. So after that, what happened? The multi-threading concept came into picture. Again, one CPU can handle one task at a time, so that is okay. But inside the applications, right? Inside the applications, the developers start creating multiple threads. So it can be thread 1, thread 2, right? So CPU will run this application, but inside this application, if there are two threads, so CPU will first run thread 1 and then switch to thread 2. Again, the switching between threads is also happening in the same way like it was happening in the multitasking, like switching between the applications. So only difference is now within the same applications multiple threads can be written by developer, so that CPU will execute the threads one by one or switch between threads so that the work can get faster. Now in modern computers, like you have like lot of CPUs, right, at one time, or you have 4 CPUs now, right? So for in this case, what will happen, maybe one thread can be executed by CPU 1, another thread can be executed by CPU 2, right? So in this case, when you have multiple CPUs in modern computing system, the multiple threads are executing at the same time. Now it's not switching because we have introduced more CPUs, but now the real parallel execution is happening. So this is the concept which all the applications use to improve their performance. So they run tasks in background. For example, if thread 1 wants to download some data from one location, so it can run in background. Thread 2 can connect to database. Thread 3 can do some other tasks, because we have a lot of CPUs now, and every CPU can handle one thread, right? So which is the main reason that in today's world the performance of the applications are too high, so they give you response in milliseconds even if you are connected to a database and you are dealing with millions and billions of data. Due to multi-threading implementation, the tasks can be done in very quick way. So multi-threading have a lot of benefits, like we are using the CPU in a better way, we are getting the response as quick as possible, but it comes with a lot of problems when you write a code for that. So for example, let's say both threads are managing the same memory, right? So if they both have same memory, shared memory model, then it can lead to a lot of problems, like deadlock can happen, race conditions can happen, congestion can happen, and many more, right? We will see all these things in the code also. So what I'm trying to say is, like, if like multi-threading have a lot of benefits, but managing the memory state and avoiding the synchronization issues is really a headache for developer, right? If it is not done in a right way, it can cause a lot of problems like data inconsistency, deadlocks, and other conditions. So now let's see in the Java how we can create the threads. If you're not familiar with the basic Java, I will recommend you go to my core Java playlist and see that video, like how Java code runs and other basic videos. So to start the new thread, right? So you can use the thread class. So what I will do, I will create object of the thread class, and I will just use object thread object. So I will use object thread dot start. Okay. So in this way, this new thread will be started, but it will not do anything. It will just start and then it will just stop, because we have not given the implementation of the run method. So now to give the implementation of the run method, what I will do, I will create here my thread extends thread. So we are here using inheritance concept. So I will here give the implementation of run method. Okay, so I will say thread 1 is run. Okay, so now when I start this thread, so you will see the implementation whatever we have given inside run method, it will get triggered. I will run this one, it will create a new thread and it will execute this statement. So this is one way of doing or creating a thread. I will not recommend you to do like use very legacy code. So we should always use functional programming and lambda expressions. So if you're not familiar with that, so you can check my this Java streams video, which will really help you. So instead of doing like this, so what I will do, so I will create thread object thread 2 is equal to new thread, and inside this I will give the implementation. So I will write the statement here, thread 2 is running, and then I will say object thread 2 dot start. Okay, so now if I will run this, so our two threads will started along with the main thread here. So thread 1 is running, thread 2 is running. So I will just remove this code. So this is just a very legacy way of doing it, which is not recommended now. So I will remove this. So here we have used lambda expression to give the implementation of the run method. Now this is also not the efficient way of creating the threads. So these days we always use the runnable interface to create the threads. So how we can do that? So I will say runnable and I will create object runnable is equal to new runnable, and inside that I will again give the implementation of run. Thread 3 is running, and then I will use this runnable task and pass it to our thread class. So I will say thread object thread 3 is equal to new thread, and inside this I will pass object runnable, and you can also give the thread name. So I will say object, so I will say runnable thread, and then again we have to use a start. Okay, so now if I will run this, so we are using the runnable interface and we are passing that to this thread object. So you will say thread 3 is running. Again here we are using the new keyword, so which is not recommended. So we can convert this code to lambda expression. So I will remove this one, and I will just give the implementation like this, and I will remove run. And now our code readability is so much better. So if you see, the runnable is functional interface. So functional interface basically have only single abstract method which is run, as the method is only one, right? So whatever implementation we are giving it here, it will automatically apply to this run abstract method. So that's why the functional interface works best with lambda expressions, because they only have single abstract method. So in this way, you can create either thread using this without runnable, which is not as efficient as creating the runnable interface and then passing that to the thread. And then we can use a lot of methods here. For example, let's say I will say thread 3 started. And then let's say we can put our thread to sleep for 2 seconds. And then we can say thread 3 completed, right? And also thread, if you're using thread.sleep, you have to use try catch, so that it will handle the exception. You can also capture thread name here. So if I will say thread.current thread dot get name, so it will give me the name. And also you can see the states of the threads. So if I will say thread dot current thread dot get state, right? So it will give you the state also. So now if I will run this, so you will see first thread 3 will start, and then we are giving printing the name, which is runnable thread, because we gave the name here. And then the get state is runnable, and then thread 3 completed. You can write your execution and you can start your thread, and you can achieve multi-threading by doing this. But here, if you will notice, right, when we are running this program, so even if this thread is taking 2 seconds, right, so the main thread, our program is still running until this thread is getting completed. So that means this main thread is not getting exit until all the threads are completed. But sometimes you have to run your threads in background without impacting your main thread, because the use case can be if you want to do garbage collection, or you just want to monitor your resources, or you just want to do some logging, right? For that background task, you don't want your main thread to wait for the other thread, right? So that's why there is a daemon thread concept in Java. So by default, these threads are not daemon threads, but we can specifically set the thread as daemon. So if I will say object thread dot 3 dot set daemon, and I will say true, right? So now if I will run this program, so you will see this 2 seconds, right? So main thread will not wait for this 2 seconds, it will automatically end. So if I will run write statement here, main thread ended. So now if I will run this, so you will see after thread 3 started, right? So it didn't wait for thread 3 completed, because you can see there is no statement here, thread 3 completed. Main thread didn't wait for this thread to get completed, right? So this is the concept of daemon thread, which can be asked in the interview, what are daemon threads, and show me the code example, like the main thread is not waiting for the daemon threads, right? So you can simply create a thread, you can just set it as true, and you can show to the interviewer that main thread is getting ended without waiting for the daemon thread. So till now, like everything is looking smooth, right? But in reality, these threads will work with the shared objects, and then the issues will start coming. Okay, so I will just modify this code. So I will remove this thread, and I will just create one more runnable. Now I will just create a new threads, object runnable one, runnable thread one, and object thread one dot start, and same I will create the other thread, runnable thread two, and I will pass object runnable two here. Okay, so now we have two threads which are running, and both have their own runnable objects, right, or runnable task. So now we need to understand what is Java memory model and how the data is handled internally by Java for multi threaded applications, right? So let's say if I create here one shared object, let's say public static object shared object is equal to new object, right? So in this case, let's say we pass this shared object here. So I will just say dot hash code. So we will get the hash code of this shared object, and I will put same line in this also, right? So now if I will run this code, so you will see both the threads are accessing from the same memory, right? The hash code is same because the shared object is being used by both the threads, right? Understand how the Java memory model works. So inside Java, so we have here JVM. Inside JVM, we will have one heap memory, and then for each thread, we will have thread stack. Okay, thread 1 stack we can say, and then thread 2 stack. So this is how Java memory model looks. So now for each thread, right? So whatever the local variables are, it will be stored in the respective thread stack. Okay, so now here I can say local 1, local 2, right? Here also, let's say local 3, local 4. So these local variables are not shared among multiple threads. They are just limited to their, so they're just limited to their own thread. So for example here, right? So let's say inside this runnable, if I will say int runnable 1 is equal to 0, right? So this runnable 1 will be stored in this stack. So this thread 2 cannot deal with these local variables of each other, right? So same way, if I will say int runnable 2 here in the other runnable, so it will be again stored in the thread stack of this thread 2. Okay, but in case of shared objects, so objects will always be stored here, right? So let's say object 1, so objects will always be stored in the heap. So let's say object 1 is there, and then object 2 is there. Okay. So now if both the threads are using the same object, so they will have reference of object 1 here, but it will point to the same location in the heap. So same way here, the reference of object 1, and it will again point to the same. So in this case, if you see, both the threads are dealing with the shared object which is present in the heap. So this is when the lot of problems start, and this is when like developers have to be really careful while handling the shared objects, because it can happen like this thread is updating the value of this, but this thread is not getting the updated value, right? So all that conditions we will see eventually in this video, but this is just to give you high level flow how it looks in the JVM. And if we combine this JVM with the CPU architecture, right? So now let's understand how these CPUs will deal with the multi-threads, right? So let's say you have one machine, and so let's say in your machine you have two CPUs. So I will just do like this. So CPU 1 and CPU 2. Okay, and you will have your own RAM, which is a main memory, right? And then each CPU will have their own CPU registers. So it will have their own CPU registers, and also they will have their own caching layer also here. So this is how it looks at the operating system, right? So now if CPU 1 is handling your thread 1, right? So it will fetch all this data from the main memory, because eventually this whole data is there, right, in main memory. And now the data will flow like first to the caching layer, then to the registers, and then once the processing is done, then it will move back to the main memory, right? So same for the thread 2. So whatever data is related to that thread, it will move up to registers. Your then logical implementation will happen, and then whatever update is there, it will pass back to the main memory, right? So the register is basically the space of each CPU, which helps in the processing, and it's faster. And caching is the layer in which the cache can be done for each CPU, and each registers and cache is always in the sync basically. So This is how it works. Okay, so now sometimes, so now if you will see, this is getting like little bit complicated, but this is the interesting part also, like how to handle multiple threads in multiple CPUs. That's what you need to learn. So now the lot of problems comes, right? So first problem is the visibility problem can come. So let's see the code example for that. So visibility problem is basically, let's say both the threads are dealing with this object one, right? And this first thread will update the data for object one, but it will stay in the caching. It, let's say it's taking some time to move that data to the main memory, and at the same time CPU2 is trying to get the data from main memory, right, for same object. So in that case still CPU2 will get the old value, it will not get the value which is updated by CPU1. So let's see how it works in the code and how we can resolve that. So let's see this example. So I have one class, and inside this class I have one boolean flag, and I have getter and setter function for that flag boolean. Okay, so what I am doing here is I am creating one thread here which will set the flag value from false to true, and it will end. Basically the that's the purpose of this thread. And so in the second thread I am having infinite while loop until or unless the flag value is true. Okay, so it will keep running until the flag value is true. So if I run this code, so if you see here, thread 1 started and thread 1 logic started. After that, thread 2 already started, and then thread 1 logic completed and flag is set to true by thread 1 in this line. But if you see here, the thread 2 is still stuck on this while loop. Even thread 1 have updated the value to true, but thread 2 have not received the updated value here. It is still getting the value as false, due to which this while loop is continuously running. So this problem is known as visibility problem. So how we can solve this problem basically? So we can use here volatile keyword in Java. So if I will use this keyword on the flag, and now if I will run this, so you will see as soon as flag is set by thread 1, this while loop is over and this statement got completed here. Okay, so this visibility problem we resolved by using volatile keyword. Okay, so using volatile is one way of handling the visibility problem. We can also use synchronized keyword to handle the same thing. So in this case, if I remove the volatile keyword here, right, and I put synchronized keyword for both the methods, right, so this will also solve the problem. If you see here, as soon as the flag is set by thread 1, the loop will end and thread 2 logic will be completed. So there are different use cases where to use volatile keyword and where to use a synchronized. So let's discuss that use cases. Before jumping to difference between volatile and synchronized, let's see how it is working internally, right? In this code example, we have one boolean keyword, right? So let's say we have one boolean keyword here, right? Now the thread 1, right, which is running on CPU1, will fetch the value of boolean, and it will process the value, like change the value here in the registers and sync that value in the caching. The updated value is already here, but it is taking time to sync it with the main memory, right? And at the same time the CPU2 thread 2 is running, so the thread 2 is not directly checking the value in the RAM, because when thread 2 started, it is also checking in the caching store, right? So registers keeps on checking in the caching store because while loop is running here, right? So with the help of volatile keyword or synchronized keyword, right, what we are saying to the threads is, like, as soon as you update the value of boolean, immediately you put back that value in the main memory. If boolean is volatile, right, we are using volatile keyword, so what we are saying to thread 2 is, you don't check the value from caching store, or you don't pick the value of volatile variable from here, you directly put, so you directly pick up the value from main memory. So that's why when we used volatile or synchronized, as soon as the value got updated here, it got passed to caching store, it got passed to main memory, and thread 2 immediately read that value from the main memory and ended the logic. So that's what happened in our code here. Okay, I have this code example. So in this code example, what I am doing is I have two threads, and inside each thread I am incrementing the count of one integer 50,000 times. Okay, and same thing is happening in the other thread, and both the threads are accessing the shared object, and inside the shared object we have increment method which is doing count plus plus. So if I run this code, so you will see like thread 1 started, thread 2 completed, but our final count is not what we were expecting, because final count should be 50k plus 50k, 100k, right? But the count is 63455. So this is known as race condition, when two threads are trying to do any operation on the shared object. So this can happen, inconsistency of data can happen in this condition. So let's see why it happened first. So if I go to this diagram, right, so I will just copy this. So let's say in our code, two threads are running. So let's say on CPU 1, thread 1 is running, and CPU 2, thread 2 is running. Okay, so it will look like this. And in our main memory, we have one integer variable that both the class will try to increment, right? So what happened is, when you think increment, right? So in increment, in the backend, three operations are running. So what will happen here? So when you say I plus plus, so first step is the value of I will be fetched or read, right? And then add 1 to the value and assign new value to I, right? So I plus plus do these three things in the backend. So it's like not a one operation, right? In the backend, it's like three operations are happening just to increment the value of any variable, or you can say even in case of decrement, same thing will happen. Instead of add 1, it will be minus 1 to the value. So when this thing is happening, that so in the code, we started first thread, which will run 50,000 times, and thread 2 will also run 50,000 times. So let's say when it ran first time, right? So let's say it's running first time. So CPU 1 or thread 1 fetched the value as 0 from the main thread, right? And then, so I will remove this. So let's say first the value is being fetched here, and then it is stored in cache, and then in the registers your I plus plus line will start implementing this one, right? So this method logic will happen in the registers, and in this logic these three operations will happen, right? The value of I will be fetched, add 1 to the value, assign new value to I. So what will happen now, like during the time this thing is happening, right? Let's say thread 2 also started, and it fetched the value as 0, right? So it fetched the value as 0, and it goes to his, and it goes to the caching, then registers, and then this registers is also doing the same thing, I plus plus, right? When this thread is doing I plus plus, then let's say this thread already performed the operation and put the value back as 1 in the main memory, right? And after some time, then this thread 2 also did the same thing and put the value as 1 in this main memory, right? So in this case, if you see, the ideal value should have been 0 plus 1 is equal to 2, but due to race condition, right, the value became 1 in the main memory. So that's why when we are running the loop, let's say 50,000 times for both the threads, that's why the count is becoming less. It will always be less, right, if we will not handle it. So now to solve this race condition, right, we can use atomic classes. So let's say if I will convert this int to atomic integer, and then I will say new atomic integer 0, and then instead of count plus plus, I will use increment and get method of this class, which will make sure when these steps are getting performed, right, when this step is getting performed, then no other thread is fetching the value, so that it makes sure every time the new thread will get the real value, not the old value, right? And instead of returning count, I will say return count dot get 0. So I will just say count dot get, and if I run this code now, right, so we should able to get the exact count. If you see 100k here, this thing can be solved by atomic classes, or it can also be solved by synchronized keyword. So let's say if I go to the same example and I will revert back this code. So I will change it to int, and then let's say instead of this increment, I will just use the synchronized keyword on increment method, right? So if I run this code now, right, with the simple int, but on increment method we are using the synchronized keyword. So synchronized is basically a lock based approach, and atomic keyword or atomic classes are non-lock based. So if you see here, the count is as expected with synchronized also, but only difference is atomic classes will be faster than synchronized in this case, because again it is like doing mutual exclusion, mutex, or you can say lock based approach, right? But atomic classes are not doing any lock. Instead they are leveraging the hardware support to perform that operations. Okay, that's why it will be more efficient as compared to using synchronized block. Synchronized can be used in 4 ways. So this is the method of the instance class, right? So we are using it like this, and also you can use on the static method in a same way. And also inside this method, like let's say if you want only to specify synchronized on particular code of lines, right? No need of synchronized, no need of logs, right? And then instead of putting at method level, you can also use it like this, synchronized this, and you will be good to go, right? So this way synchronized can be helpful, just to make sure you only synchronize that line of code in which the developers can see the issues can come, like race condition or visibility problem that we discussed in the last video. So you must check that video in which we discussed visibility problem and how we solved it by a volatile keyword. And also you can use same in the static method also. If I will say static here, so in static, instead of this you have to give the class name dot class. Okay, so it will work fine here. So, and it should be static. So like this you can use either in the static method, or you can make it whole static method as synchronized, or you can use within the static method or the instance method. So that's how you can use a synchronized keyword. And atomic, for atomic classes you have like atomic integer, boolean, long, right? And you have other array classes also, and inside each class you can use different methods like count dot increment and get, right? And then you have compare and exchange. So this is like if you want to exchange based on some value, so it can really help you. So these all methods are helpful, but most of them you can use increment and get, or decrement and get, and a dot get to get the value. Most of the people are confused like when to use these keywords. So let's see the high level use cases. So I have prepared one tabular format. Let's discuss what's the difference between synchronized, volatile, and atomic. So for mutual exclusion, synchronized is a lock-based approach. That's why it ensures mutex or mutual exclusion, but volatile and atomic are non-lock based. So for visibility, synchronized will be able to achieve that. Volatile will also achieve the visibility of changes, but doesn't provide a mutex. Atomic will ensures visibility plus atomic operations like we saw I plus plus or I minus minus. So atomic classes will handle that thing. For performance, synchronized can lead to performance overhead due to locking and context switching. Volatile have so volatile and atomic will have better performance as compared to synchronized. But volatile, only one drawback is it may not always guarantee atomicity. Atomic will give definitely better performance than synchronized because it leverage hardware support for atomic operations like CAS or read, modify, write. So CAS is compare and swap, or read, modify, write. So that's why it's really fast and it's really efficient. And use cases, right? So developer have to understand, like based on their application code, what it is doing, and use these keywords accordingly, right? So if I am a developer and I feel like I need mutex on some line of code or method, right, then I will go with synchronized. And if I feel like my code is uh, like if I have a code that we saw in the last example where one thread is updating the value and other thread is just reading the value, right, in that case you can go with the volatile keyword. And if we are dealing with some increment or decrement atomic operations, then you can always go with the atomic classes because it's inbuilt and it's non-lock based, so you don't have to worry about performance also. So these are the some of the use cases and difference between these things. So all so at the end, developers should able to know this concept so that they can use them accordingly. So it's not like these are competing with each other. It's like we have to use all three of them in our code wherever needed, right, or wherever appropriate to use. So let's quickly see the happens before concept. So basically what happen is like if in your code, right, you have some set of instructions, then CPU or compiler will automatically reorder that instructions to give you the better performance because they will run that instructions in parallel. Let's say if we have any instructions like this, let's say A is equal to B plus C, and then we have D which will be equal to A plus Z, and then we have like M is equal to N plus O, right, just a random things, right? So it can be anything like maybe full name is first name plus last name, so any logical thing it can be in your code. But here the issue is, let's say developer have written the code in this sequence, but when you run this code the compiler or CPU might reorder the things to run this line plus this line in parallel because they don't have any dependency, right? So it can be the case reordering code can execute in this way, and then in the last it can run D is equal to A plus Z because this have dependency on A which is coming from here, right? So the reordering can happen, right? So it's fine for the single thread, right, but this can cause issue when multiple threading, when multiple threads are accessing the same variables, right, shared variables. So that's why to avoid that or to give the set of instructions to the compiler, we use these keywords, right, so that reordering will not happen in a way which will impact your logic in the multi-threaded environment. So let's say if you have any web application, so let's say you have web application, and inside your web application you are making threads for each user. So I will say, let's say thread 1, thread 2, thread 3. Okay, so it can be up to thread n. So if 100 users are hitting your web application, right, at the same time, so it will lead to 100 threads. So same if 1 million users are coming, so it will create 1 million threads in your code, right? uh, so let's say you have 3 threads here, and I will just put the user icon here. So let's say user 1, user 2, user 3. So all are hitting the web application, and in the code 3 threads are getting created, and each thread now you want, like each thread should have some user ID attached to it, right? Like if thread 1 is processing the request for user 1, so this user might have some username or user ID, so you want that user ID to attach to thread 1. Okay, so one way is, as we saw in the first 2 videos, like you can make use of the shared variables, but in that case it can lead to like a lot of synchronization issues developer have to handle in the code, use of volatile keywords, synchronized blocks, atomic classes. So all that complexity comes into picture for developers, right? But what Java says is, if you have this type of requirement, you can make use of the thread local class in Java. So each thread can make use of thread local class to store their local copies of variable. So thread 1 can store user 1 in this, and it can also get user 1 from the thread local, and this user 1 will only be fetched by thread 1, and it will not be visible to thread 2 or thread 3. So it's completely thread safe environment. So same way user 2, so thread 2 can store the local copy in the thread local, and it can also get his own copy from the thread local, right? So in this way we can make use of thread local, which makes the developer's life so easy, so they don't have to handle all that shared variables issues. So in this way you can use thread local, and instead of user id it can be anything. It can be your database connection, it can be your thread context, so it can be anything you want to store which is local to each thread. So that is the main purpose of thread local. So if I will open some notes here, so thread local helps in creating variables that can be read and written by the same thread. These variables are unique to each thread and are not shared among different threads. It's particular handy in scenarios like we saw now, to handle like user sessions or database connections, user IDs, and all that stuff you can easily do with thread local thing. And it also improves performance by avoiding synchronization overhead in multi-threaded environment, because using all that synchronization things, right, lead to performance issues also, and can also lead to other issues as well. And each thread holds its own copy of the variable, so you really have to be careful like while implementing the thread local, because if the reference is stored for longer, right, it can lead to memory leaks. So that's why developers have to really careful while implementing the thread local in their code. But overall there are a lot of benefits to it. It's being used in the many real use case applications to manage the thread context or user sessions or database connections. So this is the flow of thread local. So now let's jump to the code level. So I've already written the code. So from code level, it's not that hard, to be honest. So we will quickly go through the code. So if you can see here, right? So what I am doing is I'm creating the thread local user. So I'm creating the thread local of a long type, and in the first request, if you see, I am using this thread local to set the user ID. So I have just, for this example, I have just two hard coded user IDs here. So for the first thread, I am putting the user ID using dot set method. So if I say here dot set, so if you see, when I do dot set, it already knows like it's of type long, because we already defined uh, there. So we can pass any long value here. So I will pass user ID here. And after that, your thread started. Now you know this thread is for this user ID. And then you can process your logic and all that things you can do according to your application use case. And then if you see here, you can easily get the user ID by using dot get method. So when you do dot get, right, so you are not passing anything else. So thread local knows like if this request is requesting me dot get, so I will return the copy of this thread only. So I should not return the copy of any other threads. So you can use dot get, and once your work is done, then you can always use dot remove method, right? It's very good practice to remove thread local objects once you are done with that. Okay, so if I will, after removing, if I will again do dot get, so ideally we will get a null here. Okay, so same thing I am doing it there, thread local user ID local one. So again I can use dot get here, and again I can use dot get here after remove, which will give us the null. So here, so we did, so for refresh purpose, we did three things. We first declared our thread local of the long type. It can be any type. It depends on your application use case. And then we used dot set method. Then we used dot get method. And then in the end, we use dot remove method. Okay, so these three things we used for both the threads. And once I will start, I will run this one. So let me remove this code. So we will discuss this after running this. So I will run this code, so you will able to see. So first thread started for this user, then second thread started. So first thread logic completed, then we used dot remove, and that's why it's giving us null here, right? Because after remove, if you will use get, that means it will always give you null because it have removed that from the thread local memory. And this is how it work. So hope it's clear now. So the last concept is, we in some cases we use like parent and child threads, right? So in that case we use inheritable thread local, where the parent can pass the the variables to the child class. So what I mean is, so let's say I'm creating inheritable thread local of string type, and I am starting one thread, and inside that I am setting this inheritable thread local value to Instagram. So now this value can be accessed by the child thread using .get method of inheritable thread local. Okay, so there are two things now. So one is thread local, one is inheritable thread local. So inheritable thread local value can be read by the child thread, but if I will set up only the value of thread local, right? So let's say set 1 2 3 4 5 any value, right? So this value will not be visible to child thread also. So is this value is only limited to the parent thread, but in some cases if you want child thread to also get some value which is getting set by the parent class, you can use this inheritable thread local. So if I will run this one, and if I will say here print thread local, so this will return null because this will refer to the thread local of this thread, not the thread 3 which is the parent thread. Okay, so if I will run this code, so you will see here this dot get is giving the Instagram value, right? So because it's a inheritable thread local, but user id thread local dot get is giving null because we have not set anything for this thread. Yeah, but if same line I will put it here, right, outside in the parent thread, so it should ideally give the same value. So if I will run this one, so you can see Instagram and null, and before this line got printed which is giving us this thread local variable. Okay, so this is all about thread local. So it's basically provides a way to manage and execute tasks asynchronously in a pool of threads, and it takes away all the headache of thread management, right, which makes our life as developers much easier. So at high level we have like three types of thread executor which we can create, and after this we will see the code example also. So first one is single thread executor. So it's like whenever we want to do some tasks sequentially, right, so we only need one thread in the thread pool. So for that use cases single thread executor is the best to use, because in this executor you want the task, so you want the task to be executed in some specific order, right? So in that case this helps. And next is fixed thread pool. So in fixed thread pool you can give like how many threads you want, like 5 threads or 10 threads or 15, right? And once the task is submitted, so it will be executed by one of the available threads. And if the task is submitted and all the threads are busy, right, then the task is queued until the threads become available. We will check this scenario in the code also. And then we have a cached thread pool. So in this we don't give the number of threads to the method, we directly ask the method you can control the thread pool, and you can adjust the number of threads based on the workload. So if you want to create new threads you can create, and if any thread is sitting idle you can also terminate that thread from the pool. And actually there is one more thread pool, maybe I forgot to mention here, that is a scheduled thread pool. Okay, so basically sometimes you need to execute the task based on some time interval, right? So in that case you can use scheduled thread pool in your code. So let's see first all these 4 thread executors. Let's see all these 4 methods in the code, and then we will see the other concepts of this service. So in the code I have already written 4 methods here. So first is single thread executor. So in this you will see we are not giving any other detail here like number of threads, because it's only one thread, and we want like all the tasks should be not performed in parallel because there is only one thread, right? So what will happen here is first task will be executed, then second task will be executed, then third task will be executed, so on, right? So it's like one task at a time in a sequential way. And we are using your shutdown method. Once it is done with all the tasks, I'm just using shutdown method to shut down this executor. So it will not shut down immediately, but it will let these 5 tasks, right, to be completed. But after they are completed, it will not accept any new task basically, right? So that's why we use this shutdown method. And there is also shutdown now method also, so that we will see later in this video. but this is the very basic implementation. So we are using single thread executor method, and then we are just using dot execute method, and we are just passing the, we are using the lambda expression here to submit the task by using a runnable. Okay, so we will also see like difference between runnable and callable after this, but it's a simple way. Like if you have seen the previous videos of this playlist, you know like how this thing works, right? If you don't understand this code, I will highly recommend you go through the starting of this playlist so that you are aware of this concept like lambda expression, how to submit a task to the thread, right? So okay, so now second method is fixed thread pool. So here if you see, I am giving the number as 3. So that means your 3 threads are available, and whenever the task is getting submitted, right? In this case, let's say 5 tasks are getting submitted. So what will happen? The first 3 tasks will go immediately to 3 threads, and the other 2 tasks have to wait until any of the thread is available, and then that task will be assigned to the free thread. So this is how it works. And here also I am giving the shutdown method. And the third one is the cached thread pool, right? So here if you see, I'm not giving any size of the thread, right? Like 3 or 5. So that means this will be controlled internally. If I go to the implementation of this method, right? So it is inside using ThreadPoolExecutor. We will also see that like how it is different from the executor service. So basically the main difference is it will create the threads as needed, and it will terminate the thread if it's not needed. But in the fixed thread pool, right, like these 3 threads will never be terminated even if it is sitting idle. So basically whenever any task will come, it will assign to any one of them. And the fourth one is a scheduled thread pool. So basically here we use this thread pool whenever we want to have some delay, or whenever we want to schedule task to execute after some time, right? So in that case, this can be really helpful. So if I go to the implementation of this one, so you will see here we have they are using like delayed work queue here, and inside delayed work queue they are still using blocking queue. But the point is we are also passing the delay, and we are also passing the time unit. So high level, these 4 methods, again it's very simple and basic implementation, just to show you like how these 4 methods are different from each other. So if I will run this one, so okay, so now it's getting in, now you will able to understand it more. So first let's see single thread task, right? So if I will search here single thread task, you will see here all the single thread tasks are being executed by pool 1 thread 1, right? Pool 1 thread 1, pool 1 thread 1. So which proves it like there is only one thread, right? So all the threads, all the tasks are being executed by the same thread in a sequential order. So what happened here is thread 1 finished the single thread task 1, and then it proceed to task 2, then it proceed to task 3, task 4, task 5. So if you see, the sequence is being maintained in the single thread task, and it is not happening in parallel, and there is only one thread here. So if I go to the fixed thread now, right? So if I will search here fixed thread task, so you will see here, so in fixed thread task the sequence will not be maintained, so it depends like internally which task to be executed. But one thing we know is it should only have 3 threads. So if you see, task 1, task 2 and task 3 are immediately picked up by thread 1, thread 2 and thread 3, right? But 4th and 5th were waiting in the queue, right? And then once any of these threads got free, so task 5 was picked up by thread 2, and task 4 was picked up by thread 1. So that means thread 2 got freed earlier, so it picked up task 5, and then it picked up task 4, thread 1. Thread 1 picked up task 4. So this proves like if like first 3 tasks were immediately picked up by the different threads, because thread pool size is 3, right? And 4th and 5th waited for some time, and then it picked up either by thread 1 or thread 2 or thread 3. So that's how it works internally. And if I go to cached thread pool, right, so we have not given anything here, right? The size. So ideally it should be picked up ideally all tasks should be picked up. If you see here, it's picked up by different threads: thread 1, thread 2, thread 3, thread 4, and then thread 5. So that means they immediately picked up all the 5 tasks, run in parallel and close the threads. So this is difference between cached thread pool and fixed thread pool. So, and then scheduled thread pool, right? So if I go here, so if you see here, so thread one, and the pool size is 2, right? So that means only 2 thread are there. So first tasks were picked up by thread 1, thread 2, and then there was delay, then thread 1, thread 2, then again delay, right? So that's how it works. So hope this is clear now. So this is just very basic implementation. So the idea is to give you the basic information so that you can use any one of them in your application use case. If I will show you here, right, like how it looks internally. So let's say what we did was we did pass like a lot of tasks, right? So we had like up to 5 tasks, right? So if I take this example, so where we used a fixed thread pool, so it have 3 threads, but we are passing the 5 tasks to that, right? So how it looks like, so let's say these are our tasks, right? And let's say this is our executor service, and in our executor service we have thread pool here, and inside this thread pool our size is 3, right? So it have 1 thread, 2 thread, 3 thread, just to explain, right? And inside this I will, if I will go, they are using the blocking queue here, right? So it will have blocking queue here. So what will happen is the task will flow here. So if I will say here blocking queue, and this is thread pool, how it will look basically. Task 5 tasks, 3 threads, right? So what will happen, executor service know I have 3 threads available, right, in the starting. So immediately these 3 tasks will be picked up by any of these threads, right? So this task can be picked up by this can be picked up by this. So there is no particular order, it will be decided internally, but these 2 tasks will go directly to the blocking queue because we are still waiting for the these tasks to finish this execution. So let's say this execution is completed, this is completed. So now from blocking queue, then they will pick up the task like that. So this is how it works. So ThreadPoolExecutor is a class which is used with the executor service interface, and it have 5 parameters. So let's first understand what these parameters are, and then we will run the code example. So the first one is core pool size. So core pool size means the number of threads to keep in the pool even if they are idle. So maximum pool size is the maximum number of threads to allow in the pool. Keep alive time is basically if your number of threads are greater than the core pool threads, right? For how long you want to keep that threads alive, and this is a time unit, and this is the blocking queue. So if I go to the implementation, so here I am giving the core pool size as 1. That means 1 thread will always be there even if it is idle. Maximum pool size is 5, so up to 5 threads can be opened by the executor service as needed. So keep alive time is 0 millisecond. So that means if the thread is greater than 1 and it is idle, so immediately terminate the thread. Link blocking queue runnable to store the task. And here I am giving the 5 tasks, and I am using this thread pool executor. So if I will run this, so you will see here, so 5 tasks are being executed by the same thread, right? Because our core pool size is 1, but the maximum pool size is 5, right? So the question is why the additional threads were not started by, right, a JVM? Because the maximum pool size depends on the blocking queue size or capacity, right? So until or unless this blocking queue capacity is full, the new threads will not be started. So if I will give the capacity as 2, right? So now you will see after 2 tasks the capacity is full, then immediately thread 2 and thread 3 will be started because there are 5 tasks, right? So 5 tasks, 2 are here, 1 is handled by this, then 2 additional threads got started, and then it is being used. So this is how thread pool executor works. So I have copied that code here. So let's see how it works internally, right? So this line will result in creating the thread pool executor, which will look something like this. So it will have only 1 thread which is sitting idle, and linked blocking queue with the capacity of 2, right? The buffer size is 2 right here. So from our application, when we triggered 5 tasks, right, in a loop, so what will happen? So first task will be definitely picked up by thread 1, second and third task will be pushed in the queue, right? So it will be in the queue, and then the queue will be full, right? So once the queue is full, then this maximum pool size is 5, right? So JVM will immediately start thread 2 and thread 3 to handle the task. We see the log, right? So task 2 and 3 were executed by different threads because the queue got full. And once all the 5 tasks are done, right, so these thread 2 and thread 3 will immediately be terminated because our keep alive time is 0. So producer consumer problem is a very classic synchronization problem in computer science. So basically multiple threads are producers which are producing the data items, and consumer threads are basically who are consuming these items. So if I will say, let's say I have one queue here, and it is a shared queue basically which is being used by multiple threads, and let's say I have producer thread here, so which is producing the events and which is producing the events and putting it in the shared queue, right, like this. And then I have one consumer thread, so I will put consumer thread here. So basically consumer thread will consume the events which are put in this queue by the producer thread, like this, right? So now this architecture looks okay, but a lot of problems can come. So what if, what if the speed of this producer thread is more than consumer thread? So that means the producer thread will keep putting the events or data in the shared queue, and the consumer thread is consuming that event or data in a speed which is less than the producer thread. So it can lead to the overflow of this shared queue, right? Because more data is now there and the consumer thread is picking up the data very slowly. So there should be some mechanism or controls in place in our code so that we can say to producer thread, don't send us event because queue is full, and let's wait for the consumer thread to pick the event first. And the reverse case can also happen, right? So if the producer thread is putting the events in the shared queue slowly, or the speed is less as compared to consumer thread, so what will happen, the consumer thread can try to fetch the events from the empty queue, right? So there also, before fetching the event, there should be some controls in our code to say that consumer thread should wait for the producer thread to put the event, then only it can fetch. So these are the problems which should be handled while dealing with the producer consumer problem, so you don't end up in the errors when the speed of the producer thread and the consumer thread is not matching with each other, right? So this problem can be solved with blocking queue. So if I go to the code level here, so I will show you the blocking queue example. So here I am using the blocking queue, so I am giving the capacity as 5, and I have one producer blocking queue and then consumer blocking queue, and then I'm just starting the thread, right? So if I go to the code here, so you will see I am not handling anything by my own here, right? So I am just using the put method of the blocking queue, and in the consumer I am only using the take method here, right? So I'm only using the take method, and I am only using the put method in the producer queue, right? So now if I go inside this, right, method, so you will see the implementation of this one, right? So I just go to put, so insert the specified element into this queue, waiting if necessary for space to become available. So this is the first problem that we talked, right? If there is no space in the queue, so that means producer speed is more than consumer speed, right? So in that case it will wait for the space and then only it will put it inside, right? So that means it is internally handled in the blocking queue class. If I go to the take, right, take method here, so you will see here retrieves and removes the head of this queue, waiting if necessary until an elements become available. So this is the second problem that we talked, when consumer speed is more than the producer speed. So in this case also it will wait until the element is there in the queue before picking it up. So that's how you can implement. So I will show you the code again. So I have the capacity of 5 and I am passing this same queue, shared queue, to the both producer and consumer, and the producer code is very simple here. So I am just using the put method, and then I am take, and in the consumer I am just using the take method. So if I will run this code, so you will see it will run fine. So consume 0, produced 1, produced 2, consume 3, right? So even the uh, speed is, so in this first case, right, the speed of the producer is faster than the consumer, because here I am sleeping for 2000 2 seconds, and then here I am using the speed as 1 second, right? So producer is faster than consumer, but still it will not give me exception, so it will handle everything internally. So this is how you can solve the producer consumer problem, by using blocking queue. But if you don't want to use blocking queue, right, then again you have to implement the synchronized concept here that we already discussed in this playlist. So if you are not familiar with this concept, I will suggest you start this playlist from the starting of the from the first video, so you will be able to understand. So here I am not using any blocking queue, I am simply using simple list, but I am handling that logic by using synchronized keyword and notify all, right, and wait. So if you want to use synchronized and wait and notify all, you can also use this, but it's again an overhead on the developer, and maybe the developer will have to handle a lot of manual conditions, right? So as a developer, I will not go with this approach until or unless I have some use case which blocking queue is not able to uh, solve that. But still, by using your own code, by using your uh, the multi-threading concept or concurrency keywords like synchronized, wait, and notify all, you can still use you can still solve the producer consumer problem, right? But here manually you have to check the size, and here manually you have to check whether it's empty or not. So all these conditions are already handled inside blocking queue, so that's why I will always prefer to use blocking queue as a developer until my use case is not satisfied with it, right? So here I have just written like number of threads. First we will start creating platform threads. So we know in comparison, like after how many threads creation the platform threads will give us error, and then we will start with the virtual threads. So I'm just creating here simple runnable object that we saw in the first video of this playlist. So here I am simulating some API call, but in your production code you would have some code like this by using http client, and then you are giving some API URL. So in this program you will be hitting million of times, so it was giving me the request limit maximum reach out error, because they are not allowing me to hit that many requests within a seconds. So that's why I'm just simulating some of these here inside the object runnable run method. And here I'm starting some for loop, and inside this is a platform thread. So whenever you create a platform thread, it will be tied to your operating system level. So it will have some CPU capacity and memory. It depends on a CPU capacity and memory, and if you try to create beyond some limit of CPU, it will give you some error like maximum limit reached, because every thread will also have large thread stack and other resources to manage. And here I'm just setting the name, I'm setting to Daemon true, and after that I'm joining all the threads here to see whether all the requests are getting completed or not. Okay, so I will run this with 10,000 number of threads, but threads are platform threads. So if I run this, so let's see if 10,000 platform threads are supported by my CPU machine. Okay, so here if you see, right, after 9182 threads, so approximately 9,000 platform threads, it start giving me error out of memory. So that means my operating system doesn't have that much capacity, like it can create beyond this number. So let's now try creating the virtual thread. So I will change the syntax here. So I will say thread dot of virtual dot unstarted, then I will pass the runnable here. Okay, and I will just comment this daemon true, because by default all the virtual threads will be daemon, and I am just using start method here. And but you can also directly start here also. So there are different ways to start the virtual thread. So same code, everything else is same. So I just changed this platform thread to virtual thread. So if you see, if I will run this now, so it should not give me error, and it will run all fine, right? So if you see, everything works well, all the threads were created, and all the process finished, right? So let's now increase our number to 1 million. Okay, we'll run this program again. So let's see. So if you see, till now there is no error, everything is working fine. So it's almost reached to 700k, 800k, and then it almost reached to 700k, and the data is getting fetched. And if you see, this is our 1 millionth thread which got completed. So within some seconds, right, I was able to play with 1 million threads. And I believe, like, if we give 10 million also, so let's try. So I will give 10 million here. So if I run this also, it will work well, because it's really lightweight and it is not using much of the operating system resources. It is running at the JVM level. So if you see now, it might take some time, because 10 million is a huge number. But what I'm trying to show here is it's still working. It is not saying that, like that, it will give you error. So if you see, it's still working, and I think it will get completed also. So till it is working, right, because 10 million will take some time, but it's almost reached up to 3 million. So till then, let's see some theoretical information of virtual threads. And if I go to this Oracle documentation, so you will see why use virtual threads, right? So we only have to use virtual threads where you have great number of concurrent tasks that spend much of their time waiting. So this is a really important fact when using virtual thread, where you are waiting for database operation, waiting for the file thing, waiting for the API call. In that case, virtual threads should be your solution in your code. Be clear that virtual threads are not faster threads. So they do not run code faster than platform thread. So the only purpose of them is to provide scale, not speed. Okay, so it's not for speed, it's for scaling higher throughput of your application. So that you should always remember. And if you see here, the single JVM can support millions of virtual threads. So we saw now we were able to run 10 millions. Maybe if we increase to 20 millions, we should able to create much higher than that. And they are not intended for long running CPU intensive operations. Okay, so wherever there is some logical thing, you should always go with platform thread. You should not use virtual thread in that case. And we already used this of virtual.name.start, then runnable. And we can also use thread builder here. So you can create thread builder. And in the last video we already saw the thread local concept, right? It is possible to use same concept in this virtual thread also, so that each virtual thread can have its own copy of thread local variables. And you can also use executor service here, and same thing is available for platform thread also, only the method name will be different. New virtual thread per task executor. So if you have watched entire video till now, I hope your concepts will be clear. So let's quickly see what are the important interview topics. So most of them we have already covered in the all the concepts, but I want to give a quick overview. So the first one is a difference between process and thread. So it's quite simple. So we have already covered this in the basic concurrency concept, right? And then we have already covered how can we create a thread in Java. So this is already covered here. And then the third one is describe the different states of thread. So this is quite theoretical and simple concept. So whenever you start any thread, so there are different states. Like when you create a thread, it will be in the new state, right? And in this state, the thread has been instantiated, but the start method has not been called. Next will be runnable. So after calling the start method, the thread moves to runnable state, and then it is running. So when the thread scheduler selects the thread from runnable state, it enters the running state. So in this state, the thread code is actively being executed by CPU. Then blocked or waiting. So thread enters the block state when it is inactive for short time, because it is waiting for some other resource or condition to become available. So it can be either IO operation or waiting to acquire a lock. And then timed waiting. So thread can also enter a timed waiting state when they pause execution for the specific period. So it is basically when you use sleep or join, right? So that's the time it is entering into this state, timed waiting state. And then terminated. So final state of thread is terminated, which means the thread has completed its execution and will not run further. The real use case, if you have to relate to the theoretical part, like if you are building a chat application, so each user interaction with the chat interface, right, is handled by a separate thread. So the thread state will change. Let's say first it is a new, when the new user opens the chat application, then runnable, once the user logins, their thread transition to a runnable state, and then it is running when the scheduler selects the user thread for execution. And then it is a blocked when user sends a message and it needs to send over the network. The thread might enter the block state while waiting for the network IO operations or any other operations, basically waiting for some resource. And once user logs out or closes the application, their thread enters the terminated state. So this is high level thread life cycle. So most of the times it will be asked in the interview, so they just want to see your knowledge, whether you know about a runnable state, running state, and how the thread is getting completed, right? So entire life cycle. So this is the diagram here. And then another important question is, what is a daemon thread? So that is also mostly asked in interview. So basically the daemon thread is like which will run in the background. So in the real use case or real production application, we use daemon threads, like let's say for logging or for monitoring, because they are not dependent on the main thread, right? So it doesn't prevent the JVM from exiting. So that's the purpose of daemon thread. So they are automatically terminated when all non-daemon threads have exited or entire JVM is shut down. So the real use case is garbage collection, monitoring service, background tasks. So whenever you need any background task, you don't want to interrupt the main thread. So that's the use of daemon thread, and it is used heavily like in infra applications. So whenever you want logging, sending periodic heartbeats, right, and cleaning up temporary files. So if you have some thread which will check after every 1 hour, if the, let's say, the file size is increased, so it might clear some of the things from the, it will clear or delete the temporary files, because all these tasks doesn't require the dedicated user thread. So these are all running in the background of every application. For daemon thread, you just have to set daemon as true. So the JVM or Java knows that this thread is set as a daemon. And then we have already covered this one, runnable and callable. We have already covered Java memory model. So we have already covered data race condition and visibility problem. So we have already covered volatile, atomic, and synchronized keyword, which is very important. So this, and we already saw like what are the different features for each of the keyword. Then I think we have not covered deadlock, livelock, and starvation. So high level, you should be aware about the concepts, even if in interview they might not ask you to write a deep hands-on, but from the multi-threading perspective, right, you should be aware about these conditions. So deadlock, I think most of the people will be aware, like when two or more threads are permanently blocked, waiting for each other to release resources. So it is basically leading to circular dependency. So the real use case, like will be like you are asking your company to increase your salary, but your company is asking you to do more work first, right? But you are asking like, I will do more work if you will increase my salary, and they are asking you first you do the work, then we will increase your salary, right? So it's like a circular dependency between you or between employee and employer. That's why the salary hike will never happen. So this is a real use case. So thread A locks resource 1 and waits for resource 2. Thread B locks resource 2 and wait for resource 1. So both threads are waiting indefinitely, same as our salary hike. So prevention strategy. So prevention strategy will be like always acquired lock in the fixed order. Then timeouts, you can implement or use a try lock. And then deadlock detection, right? So you can use a tool like ThreadMXBean to detect deadlocks in Java. So the next condition is livelock. So I'm just covering it in a very crisp way, because this video is mostly for your quick interview refresh. So that's why I'm covering in a crisp manner, so that at least you are able to give answers in interview. So livelog is like basically when thread keeps changing states in response to each other without making any actual progress. So real example will be, let's say you are in a any road or corridor, right? So both people are trying to pass, the hallway is narrow, so both step aside at the same time, then move back, repeating indefinitely, right? So system is not blocked, some activity is happening, but there is no progress, right? So that's what we call it as a live lock, when two threads are working, are not blocked, but they are not progressing, right? So to prevent that condition, you should always introduce random delays wherever applicable based on your use case. You can ensure the fallback mechanism to break that cycle, and you can also use message passing. So you can use event driven state, so which will avoid live lock condition. Then starvation, so as the name suggests, like when the thread is denied access to some resource because another high priority thread is executing or using that resources, right? So example, the low priority thread is never scheduled because higher priority threads keep running, so that we call it as a starvation state of the thread because of the priority. So prevention is always use fair scheduling policies. You can also use a reentrant lock, right, for fair access to locks, so that you can use then priority adjustments you can do and avoid starvation prone algorithms. So this is also an important point. So all these conditions really depends on your use case. So most of the times, if your use case is very simple, these conditions should not happen. But if your application is really like multi-threaded heavy application, so these all things will come into picture, like you have to use a fair scheduling policy, you have to prevent deadlock by making sure the acquire, you are always acquiring lock in the fixed order, then you have to use try lock, then you have to use random delays, you have to use event driven. So all that things will come in very heavy multi-threaded applications. So real world use case like data deadlock, we all are aware, like in database transactions, two queries are trying to lock the rows in different order. Livelock can really come in distributed systems, and starvation scenarios mostly come in web servers where we have like threads of high priorities and lower priorities. Mostly lower priorities belongs to background task, and higher priority belongs to the user API request, right? So all that things can cause the starvation, which can lead to starving low priority background task. So this is a very quick overview for this question, and this question is very important also. Then Java executor service we already saw in the video, and then executor services we already saw, and producer consumer we already saw, right? So ThreadLocal already saw. So most of the scenarios we have already covered. So I think virtual threads also we covered, and then I think fork join framework. Yeah, so let me explain this in crisp way. So basically fork join framework, right, it is designed to efficiently parallelize divide and conquer algorithm where the problem is recursively split into smaller independent sub problems, and then that sub problems can be solved in parallel, and then it can be combined to form the final result. So this is a fork join framework of Java. So I will not go too much into detail in this video. Maybe I will create another video explaining about this. But high level, you should be aware, like, for example, how it works, right? So let's see how it works. So main task, let's say you have any task, you will submit to fork join pool, right? And then internally, the task divides itself into smaller subtasks, which we call it as a forking. Then the third step will be each subtask is executed independently in parallel. And once all subtasks finish, their results are merged to get the final output. So if you would have used a future, completable future, we have dot join method, right? So it is similar, so you can relate to that. And if the worker thread run out of task, it steals work from busy threads, right? So that's why, like, the whole goal of this is like to divide and conquer, right? So that's what the main algorithm is of fork join framework. So advantages is parallelism, load balancing, scalability. But you should never use fork join for a simple use case, because if you use fork join, and I have tried that a small POC, when I'm using fork join pool versus I'm using simple threads, fork join pool can take longer time because creating the threads, managing the threads is really overhead to the JVM. So if you're trying to use fork join pool for a simple use case, your performance will reduce. So it will not help you, but it will delay your processing. So I have done a lot of POCs on that, and I have found out like it is really not at all helpful for a simple use case, but it's good to learn basically. Basically, it is an array, and then we are starting the common pool, and then we are just invoking the sum task. So if you see this one, if the range is large, split the task into two subtasks. Then dot fork will execute the task in parallel, and then dot join will join the task. So basically, split, process in parallel, and then join and give the final result. So that's the main, very simple language. So if you will really explain in simple language in interview, it will give you more good points, because if you're using too theoretical language, sometimes it can backfire you. So just try to explain in very simple language: fork and join, divide and conquer, simple. And then I think we already covered, so I think this is already good. So most of the topics we have already covered, so you can check out this study kit, or maybe it's a complete study course where you will get all the topics here related to Java and Spring Boot. And we also have a healthcare system project where we are diving deep into Dockers and Docker Compose and Spring Cloud. So you can check out on hungrycoders.com, and it will help you really to prepare for the interviews, and you can highlight also the points like I am doing, so that it can help you in quick revision at the last moment. So if you found this video helpful, don't forget to like, subscribe, and hit that bell icon for more programming content.